Everyone, this is Evangelos Kanoulas from the University of Amsterdam. This is SCAI 2021 Search-Oriented Conversational AI. We're very excited. We have a fantastic program this year. And this is the first session, the session on evaluation through simulations. We have four fantastic speakers that will talk about evaluation, meta-evaluation, and user simulations for conversational AI. And I would like already to give the word to the first speaker, Zeyang, that will talk about meta-evaluation of evaluation metrics. Zeyang Liu, you can share your slides, and the floor is yours.
Thank you. Okay, let me share my screen. Hello?
Oh yeah, all good. Can you share your slides?
Yeah, I'm sure my slides, but it doesn't display the. Yeah, okay. Okay, thank you. Hello everyone. My name is Zeyang Liu, and I'm a PhD student at the University of Nottingham. My supervisor is Professor Ke Zhou. It's my pleasure to share my work in this meeting. The topic of our work is a meta-evaluation of conversational search evaluation metrics. I would introduce my work within 4 parts. First, with the rapid growth of speech technology, conversational search has become popular. Here we can see this is a traditional search example. In a traditional search, we can find there are 10 blue links and titles abstract, and the user can click the result and find their information. But in the different from the traditional search, conversational search system expect user to describe their search task, use natural language, and present the search result through the conversation. It should be noted that the core of the conversational search is still an information retrieval system. So the goal of the conversation search is to seek information and satisfy the user information needs. However, there are some limitations in the existing metrics, especially in the conversational search. Here is an example. We can find that for Model 1, Model 2, Model 3, they provide different quality of response. But they for the human scores, they will annotate different quality and distinguish the quality of this response. But for some of the results, some of the automatic metrics, we can find, for example, EA, it cannot distinguish the Model 1 and the Model 2's qualities in this scenario. And the BERT score always have limited performance in this scenario. So in our work, we would like to analyze the representative metrics in conversational search and meta-evaluation their performance. First, we will analyze a single response in a single response. So we analyze what overlap-based, embedding-based, and learning-based. And we also consider the multiple response. In this scenario, that means the system provide a rank list to one question. It like always provide a rank list to answer this question and ask a user to click the link to navigate the website. And for the multi-term, we will analyze the session-based metrics in the session search. So this is the strategy. And the basic ideas of existing metrics is to compare the similarity between the candidate response and the reference or ground truth. They here example. Here is a blue's example. We can see that they will compare the reference and the candidates overlapping words, such as 2 weeks weapons, and they calculate a score based on their overlappings. So this metric have weak correlations with human preference, and they also fail to capture the syntactic structures. So in our meta-evaluation work, we will analyze reliability of the matrix fidelity and intuitiveness. In terms of reliability, this means that the ability of a matrix to detect actual performance difference as opposite to those observed by chance. We will analyze a single turn response and a multiple response. And fidelity, this means that the ability of a matrix to measure what it intended to measure and agree with limited user preference. For the intuitiveness, that means this indicates the abilities to capture any properties deemed important in a metric. So in terms of intuitiveness, we also consider the adequacy, fluency, and informativeness. For the multi-term, we will focus on the fidelities. Okay, let me briefly introduce what's the discriminative power. This power describes the consistency and the reliabilities of metrics. The basic idea is that given two metrics, metric 1 and metric 2, we will give two systems, and system X and system Y, and we will compare this performance based on metric 1 and metric 2. We will calculate the significant test and compare the p-value to tell which metrics can significantly detail these two systems' performance. So if the p-value is smaller, the metric 1 is better. Okay. Let's move on the predict power. This power describes the ability of a user to predict the user preference. That means user matrix judgment is consistent with the human judgments. Here is the basic ideas. Given two response 1, response 2, we will give these two response to human and the matrix to give a score. If the human and the matrix agree, candidate response 1 is better. That means the correct at 1. So this is calculate the consistency between the matrix and the human preference. So in our experiment, what we found is here. For the single response, we found the meta and the butter score can perform better, and the RBP is the best in the multiple response. In terms of fidelity, butter rubber is better, and for intuitiveness, the blue meta butter rubber also can achieve a good performance. So for overall performance, we recommend meta and the butter rubber because they can achieve a general general good performance in a conversational scenario. Okay. We also perform a preliminary study based on our meta-evaluation, because we found existing metrics have some limitations in conversational search. So here we propose a very preliminary matrix. Post score is a very simple matrix. Just use the post distribution to describe the adequacy of the candidate response. Here example, we can find that here always the information, useful information always hidden in the post words, such as verb and noun. So we calculate the distribution of the between the reference and the candidate response, and calculate the post score. So based on our analysis, we found our post score can always achieve better than the other existing metrics. Okay. So to sum up, existing metrics have limitations in conversation. The metrics are all original design for the other domain. This is the main reason. And always the machine translation and NL, natural language generation. They have a limits reference, but they in conversational search, we always have unlimited possible response, and they always have a complex context information. And another reason is a complex search environment. We always have multi-round interactions, and the information needs always hidden in the conversation. And also the low correlation between the metrics and the human preference. So for the future work, we focus on the context-aware metric. That means we will focus on how to use such as post features or other features to incorporate the context information, and use the reference and unreference two part to get the better performance metrics. And we also need to consider the information needs in conversation. Okay, that's all. Thank you.
Thank you very much. Thank you very much, Zeyang, for a very interesting talk. There is a number of questions, but I think we should take them offline on some clarifications about what is meant by multi-turn metrics, single-turn metrics. I think you also have an interesting paper on TOIS that people can read. So for the purpose of staying on time, I would like to take those questions offline and move to our next speaker, Aldo Lipani from University College London. I see your slides, but I don't see you. Oh, there you are. Okay, the floor is yours, Aldo.
Hello, everybody. So thanks for the invitation and the nice introduction. So I'm very happy to present you our most recent TOIS paper titled How Am I Doing? Evaluating Conversational Search Systems Offline. So this is a joint work with Ben Carton and Emine Elmans. So what we are trying to achieve with this work is basically creating a methodology to build test collections for conversational search systems. And in this paper, what we provide is a methodology for building test collections with relevant judgments. We provide an evaluation measure based on a user interaction model. And because this user interaction model requires parameters, we also provide an approach to collecting user interaction data in order to fit this model. Now, before presenting the solution that we found about building test collections for conversational search systems, let's first have a look at the way we are currently evaluating conversational systems. So the one that we'll now discuss, so the technique that we now discuss is basically the one that is currently used, for example, in the TrackCast at the moment, which is which basically uses a sequence of fixed questions coming from the user. And now imagine we have two systems. We have system A and system B, and they have produced a conversation about a common information need. In this case, the information need is about finding flowering plants that work in cold climates. Now, if we look at the conversation generated by system A, we see that the first answer to that question is pences, right? Which is a relevant answer. Then the second question is about how much cold can pences tolerate. And again, the system replies with something that's relevant. It's again about pences. And the third question is about whether they can survive frost. And the system replies with something that is relevant. Now, let's have a look at system B. So in system B, for the first question, this time, the system replies with something that is also relevant, but it's about yarrow. So it's another kind of plant. And then, because of the fact that we are keeping the interaction fixed, the user asks whether how much cold can pences tolerate. So the conversation went back now to pences. Now, if we kind of have developed a sense, we start thinking about these conversations, like the first conversation, I would say makes more sense, right? Because it's logical. There is an output that's coming from the system. The user is learning about that output, and it's refining the information needed to discover maybe new information about that particular thing that has just learned. While in the second case, the conversation has a kind of a disconnect between what the system has returned and what the user is asking. Therefore, if we were to analyze this second conversation, we would find this in a data set, we would think that there is some sort of bias happening here. So there is a problem in this conversation. So what I would say is that the first conversation is more satisfactory than the second one. Now, if we use traditional approaches to evaluate these systems, because they have returned every time a relevant answer, we would basically judge both systems equally well. In fact, we would score them the same, and by doing this, we wouldn't be able to discriminate between a system that is maybe more capable of guiding the user towards a better experience or better satisfaction of the information need. Now, how do we solve this problem? Well, a potential solution to this problem, so which basically is to weight less those conversations that are less likely, could be to just get the systems, deploy them to a large user base, and start logging what the user are doing with our systems. Of course, this is not something that academics can really do. So we like to develop, to build test collections instead. And also, if you are a large company and you have the possibility of deploying this conversational system to your large user base, this would kind of defeat the purpose of a test collection-based evaluation, which is basically getting a conversational system that already has some abilities, right? And it's already quite good. And in order to mitigate the experience that your users may have with this conversational system. Now, the question that then we try to answer in this paper is whether we can simulate this. And of course, the answer is yes, otherwise we wouldn't have had this paper published. And the way we simulate this is by looking at the literature of information retrieval and discovering that this problem has already been tackled in other information retrieval issues. In particular, we look at diversity and novelty and session and task-based track. And the idea is that the idea is to abstract queries and paragraphs to subtopics. And by doing that, we no longer need to understand the paragraph and the query. We just need to model the transition between one subtopic and the next. And here we have the examples that we just discussed before, and a third one where this time the conversation feels more natural because it's all about yarrow. Okay, now how do we do this? Well, we developed a user model, which is based on the flowchart that you see on the left-hand side. And this user model basically works in this way. Like there is so we assume that there is a user that has an information need, so has an idea, selects a potential subtopic to investigate, then generates a query. This query is submitted to the system, and then based on whether the answer that has been retrieved by the system is relevant or not relevant, it will decide whether to continue selecting a new subtopic or end the conversation. Now, the problem here is how do we model the transition of the subtopics? We do that using the probabilistic graph that you see on the right-hand side, where we model every subtopic as a node and every transition from one subtopic to the other as an edge. Okay, therefore, if we want to evaluate a conversational search system that takes as input questions and queries and returns as output answers in the form of sentences or paragraphs, the ingredients that we need for this test collection are a set of topics, a set of subtopics, user queries that model subtopics, transition probabilities between subtopics, and a corpus of answers, and a set of relevance judgments of answers to subtopics. Now, the first two requirements, so topics and subtopics, and the last two, corpus of answers and relevance judgments, these are things that we already know how to do that in information retrieval. The problem becomes how do we collect the queries and how do we calculate the transition probabilities? Well, for this, we provide an approach which is based on crowdsourcing to get this information. Now, it sounds like we are going back to the problem of deploying the model to get this data, but actually because we are treating each subtopic independently, we can crowdsource them quite easily without the need of having lots of conversations with the users. I mean, the way that we would have had otherwise. Now, the evaluation metric that we develop is called expected conversation satisfaction. What this so this evaluation metric doesn't look like a standard evaluation metric. So it's not written as a formula, but it's actually an algorithm. And what this algorithm does, it implements the simulator that I just described in the flowchart, and also it computes the score. So it evaluates the conversation. Now, for this algorithm, we provide two variants, which basically change in the way the line 16 of this algorithm is implemented. So one is called relevance independent, and the other one is called relevance dependent. And the difference is that the transition to the next subtopic in one case is dependent on whether the answer is relevant, and in the other case is independent. Now, here we have the results. So these are all, so this is the main result, and these are all simulated metrics. The difference between P, RBP, and ECS is the user model that is used. So, of course, for P, we are using the user model assumed in precision. For RBP, the user model assumed in rank bias precision, and ECS is our user model. And what we find is that using ECS and using the relevance-dependent transition, we correlate strongly or stronger with the satisfaction. And on the right-hand side, you can see the Kendall-Tau and the Spellman's-Rho coefficient, which are higher than the other cases. Okay, in summary, I hope that I made the case that evaluating conversations offline with test collections is hard. In this paper, we have used insights from diversity, novelty, sessions, and tasks to design an evaluation framework based on simulation. We have also provided the results based on subtopics and relevance. We have also provided a way to crowdsource this data to build the test collection, so to get the queries and also compute these transition probabilities. And I hope that with this paper, we have made evaluation with the conversation like the offline evaluation of conversational systems less hard. Thanks.
Thank you very much, Aldo. We do not have much time for questions, but I will ask one for you to think about towards the end. And it's about the motivation of the simulations, because typically when we evaluate these systems, we freeze the history. If you want to evaluate at turn 2, you freeze the history of the first turn. So in practice, we never evaluate in this wrong conversation you saw at the beginning. Would a system built on your evaluation be different than on a frozen history evaluation? That's the question to be answered at the end. Thank you very much for now. And I would like to invite our next speaker, Alexandre Salle, who will also talk about user simulations. And the floor is yours.
Thank you. So I'm Alexandre Salle. I'm a PhD student here in Brazil. Today I'll be studying the effectiveness of conversational search refinement through user simulation. This is work that was done in 2019 with my collaborators Shervin Malmasi, Oleg Reklenko, and Eugene Agerstein during an internship at Amazon. So personalized information agents are becoming ubiquitous, and users increasingly expect to engage in information-seeking dialogues rather than formulating a very precise query upfront. And so these user queries often underspecify the search intent or the facet of the information need. And a conversational search system can ask clarification questions to refine the set of possible intents, ultimately to improve the relevance of the search results. Here we have an example conversational search refinement session where the user inputs the underspecified query Korean language, and the system is going to try to refine the facet. So are you looking to find resources on translating Korean to other languages? And the user will say no. The user can, rather than answering just a simple no or a Boolean answer, can return more information. We call this an informative no. You can say, no, I just want to know a few common Korean phrases. It's guiding the system towards its intent. And finally, once the intent is known, we can submit an augmented query to the IR system to return more relevant results. So some applications, search refinement is very natural for voice-based agents like Alexa or Siri, where you can't return a large number of results like you can in normal web search. Understanding the intent is critical. And in applications such as e-commerce, successive search refinement is also very natural in narrowing down the choice of products using facets of the target item. There are some challenges in evaluating these systems because it usually relies on human participation for developing, training, and evaluating different variants of a system. So if you want to evaluate your system with a wide array of users, you have to do so with a large number of users or crowd workers, and this has been the dominant strategy so far. So the goal with our work was to re-examine the underlying assumptions of conversational search and more specifically quantify the effects of user cooperativeness and user patience on conversational search refinement. So rather than performing costly human evaluation with users that have different cooperativeness levels or different patient levels, we created a user simulator that can take on different personas. So we call it CoSearcher, and we use it to perform very extensive simulation experiments that would not be feasible with human participants. It only has two parameters, cooperativeness and patience. But we believe that this forms an acceptable proxy for scalable evaluation, and that it reflects realistic configurations of complex latent search variables that might manifest themselves as varying cooperativeness or patience. So here we have what's the previous, what the system looks like using CoSearcher rather than real users, and it looks like exactly the same. So it's just rather than having a human being input topics and answer questions, our user simulator is asking the system's clarification questions. Here's the big picture of what the whole system looked like, including CoSearcher. So we have CoSearcher submits a query or topic to the system. The system has a facet provider. It will determine what are some possible facets for that query or topic. It will store these in a database. It will rank these according to the current dialogue context. It will generate a question. So a clarification question. Are you looking to find resources on translating Korean to other languages? And taking into account what the intended what the search intent is and what the incoming question is, co-searcher will answer with a yes or a no. In this case, it answers with a no, and then back to the system now. The system will use that answer to re-rank facets and ask more questions. Here we have this idea of the informative no, where the user, rather than just saying no, is giving us more information. We'll extract that information and store that in the dialogue context, and that will be used for better ranking candidate facets. And finally, when we do get a yes, we augment the initial query with whatever we think the current the best matching facet is, and we'll submit that as input to the search system. So we use two facet providers in our paper. One is just human annotated facets. These come from Trek. And we also perform dynamic facet generation, where we take the initial query and we make a call to Bing auto-suggest API. And this gives us back 8 query completions or 8 facets for the topic. We also do that in the form of a breadth-first search, where we take whatever query completions Bing returned, and we use that to make another call to Bing to get yet more possible facets. So we call this B-Bing or Big Bing. For facet ranking, that is looking at the current dialogue context and the database of candidates, determine which are the most likely. We compare 2 strategies. One is just a random baseline that orders facets randomly, and the other is a very simple semantic similarity strategy that looks at the cosine between the current dialogue context, so answers that we've gotten back from the users, and the candidate facets. And we just do this using mean backup vectors as the sentence embeddings. So the heart of our system is this yes and no classifier that takes in as input a topic, an intent, and a question, and returns a score between a 0 and 1, or whether that question matches the intent or not. And then the yes and no is decided using a threshold. And this can be determined using downstream performance or just intrinsically evaluated if there is labeled yes and no data. For the training data, we use the QLAC data set. This looks like this. It has topics such as Korean language, and these are the same topics from Trek. It has intents, so what are some common Korean phrases? And then humans generate possible clarification questions that a system might ask. So in this case, the question is, okay, are you looking to find a Korean-English bilingual dictionary? And a human looked at the topic, that intent, and that question, and wrote down this answer. No, I just want to know a few common Korean phrases. Here again is an example of a human question and a human answer. So we take this data and we generate training data for a yes or no classifier. So we look for a yes and no in the first 3 words of the human answer. And if it's a no, we label that as 0, and if it's a 1, we label that a 1. And now we have training data for our classifier. Here's the PR curve for the classifier, and the F1 is 0.63 at a threshold of 0.5, and we just stick with this default threshold for all the other evaluations. So a user can have varying cooperativeness. So they can provide more information when they receive a question, and we call this a more informative answer. So an uncooperative user might simply say no, where a cooperative user might say no, I want to know a few common Korean phrases. So we define a user's cooperativeness as a Bernoulli random variable. So a user that's not cooperative will have that set to 0. A user that always returns informative answers will set that to 1. And at every turn of the conversation, we sample from this variable, and we determine whether the answer should be cooperative or not, or informative or not, sorry. And the informative responses can be provided by making use of label data from, as we have with the QLAC data set, so we can return human answers in place of as informative answers, this is a possibility for future work. And there's been, since this paper has been published, there has been some work on this, train a generative model to return informative answers. A user can also have different levels of patience, which might be exceeded when the conversation exceeds a predefined number of turns. This corresponds to the maximum amount of effort that the user is willing to spend by interacting with the search system. Here's one of the experiments from the paper. There are many more in the paper, if you guys will like to have a look at that. But in this case, we're just varying both patience and cooperativeness. And we're using the big facet provider because these pose the hardest facet identification problem. The number of facets for each topic is much larger. And so a deeper conversation is required to narrow down candidates. And we see, as one would expect, that both cooperativeness and patience are required to achieve maximal IR performance. We quantify this, and if you'd like to know more and see more experiments, please look at the paper. So finally, our contributions were, we systematically investigated the task of conversational search intent clarification. We created a simple yet powerful stochastic user simulator called CoSearcher that has these two key parameters of cooperativeness and patience. We demonstrated using extensive simulation experiments that modeling both cooperativeness and patience of the searcher is fundamental to the success of a conversational search system. And all of this required evaluating results with hundreds of thousands of parameter combinations for our experiments. And this would not have been feasible with human participants. So that's it. If you have any questions, please email me or ask now.
Cool. Thank you very much. Thanks. Thank you very much, Alex. I have only one question, and I want you to be non-cooperative, so yes or no. Could you expand your hierarchy of facets? Could you expand your facets into a hierarchy so when you get a yes, you can continue the simulation?
That for future work, yes.
Okay.
We've considered that. It's possible, but there's work there.
Yeah, of course. Okay, cool. All right, let's then thank you very much, and let's move to our final presenter today, Hsien-Chin Lin from Dusseldorf, who will also talk to us about simulations, and the floor is yours.
Hsien-Chin, you're muted. You need to unmute yourself.
So now can you hear me?
Yes.
Okay, thank you. Yeah, today I like to talk about the domain-independent user simulation with transformers or task-oriented dialogue systems. So how to find a proper environment when you want to train a dialogue system by reinforcement learning. Training systems with real users is time-consuming, and optimizing systems with noisy feedback from real users is unstable. So how about training from a corpus? The dataset is not interactive and only includes a limited amount of trajectories. In other words, it is not feasible to explore all possible paths because training with real users and collecting corpus takes lots of money and time. Therefore, training with user simulators, a more efficient, controllable, and interactive environment, is widely used in research, especially rule-based user simulators. However, you may find out their behavior is quite different to real users. In addition, you need to rewrite the rules carefully when you want to expand your model to new domains. Writing the rules takes lots of time, and designing rules for complex scenarios is very challenging. On the other hand, the statistical user simulators can learn the user policy from datasets, but they are still domain-dependent, which means you need new labels, you need to modify the feature representation, or you need to retrain the whole model when moving these models to new domains. We view user simulation in a task-oriented dialogue as a sequence-to-sequence problem. which means the user model predicts the value of each slot in the input sequence. In addition, the model should be domain independent so that it can generalize to new domains easily without modifying or retraining. Thus, we propose a transformer-based user simulator, TOIS. Let's take a look at its structure and feature representation. The input sequence is composed of slots from the user goal and the slots mentioned by the system. The order of the slots takes into account the user's priorities. A slot placed before another one means it is more important. The previous turns are also presented in the input. The whole sequence starts with a spatial token CLS, and there are separator tokens between each turn sequence. The input feature of each slot is represented by statistical features. For example, whether the constraint slot is fulfilled and which type of the slot belongs to, a constraint or a request. In some cases, multiple slots may share the same statistical feature, and it makes the model difficult to distinguish one slot from another. Therefore, we give each slot a dialog scope identity. This identity is generated randomly, and the slot has it just for the duration of one dialog, which means it can be changed in other dialogs. In this way, the model can still distinguish between slots even if their other features are similar. The output target is also domain independent, instead of predicting which value belongs to the slot. The model predicts where the value comes from, for example, copying the value from the user goal or the system state. Because the model is domain independent, you don't need to modify the input representation and output target when adapting to new domains, adding new slots or new values to the ontology. In other words, TOIS can transfer to new domains without redesigning the future representation or retraining the whole model. We train our model on the Multiverse 2.1 dataset. During the training and testing with dataset, we order the slots in the input list based on the corpus, which means a slot is before another one if it is mentioned earlier. For inference without the dataset, such as when using TOIS to train a dialog policy, the order of slots is randomly generated. User simulators are designed to train dialog policies. Thus, a better user simulator should result in a better dialog policy, which means we can evaluate the user simulated based on the performance of the policies. We train different dialog policies by proximal policy optimization, a simple and stable reinforcement learning algorithm with a rule-based baseline, agenda-based user simulator, a data-driven baseline, variational hierarchical sequence-to-sequence user simulator, and the proposed model, TOIS, as user simulators. To test the ability of TOIS in handling unseen domains, we remove one domain during supervised learning of TOIS. When training dialog policies, the user goal is generated randomly from all possible domains. Some domains like restaurant and hotel share the same slots, such as area, name, and price range. The corpus also includes domains that are quite different from the rest, like the train domain, which contains many time-related slots such as arrival time or departure time. We use direct and indirect methods to evaluate our model. With direct methods, we measure how close our model can fit the dataset. Using indirect methods, we use cross-model evaluation and thus demonstrate the generalization ability of the policy trained with a particular user simulator when evaluated with a different user simulator. In addition, we implemented a zero-shot transfer experiment to evaluate how well TOIS can handle unseen domains by leave one domain out training. We also performed a human evaluation. Policy trained with different user simulators were evaluated in interaction with paid users. The policy trained with TOIS performs well when evaluated with the agenda-based user simulator, with a 10% absolute improvement in the success rate over its performance on TOIS. On the other hand, while a policy trained with the agenda-based user simulator performs almost perfectly when evaluated with itself, its performance drops significantly by 35% when this policy interacts with TOIS. The variational hierarchical sequence-to-sequence user simulator is neither able to train nor to evaluate a multi-domain policy. We suspect that this is due to the fact that this model was designed to operate on a single domain and does not generalize well to the multi-domain scenario. Then, when we evaluate policy trained with different user simulator in interaction with humans, the success rate measures whether the given goal is fulfilled by the system. And the overall rating grades the system's performance from 1 to 5. TOIS is able to achieve a comparable success rate as the agenda-based user simulator without domain-specific information, and even scores slightly better in terms of the overall rating. For leave one domain out models, the performance of TOIS no attraction is similar to that one of agenda-based user simulator and TOIS without a statistically significant difference. We do, however, observe a significantly decrease in the success rate of TOIS no hotel when compared to TOIS and agenda-based user simulator. This is unsurprising as the hotel domain accounts for around 40% of the training data. For both TOIS no attraction and no hotel, the success rate on the domain attraction is comparable to TOIS and agenda-based user simulator. Both the success rate on the domain hotel is relatively low. In other words, removing a domain does not decrease the success rate in the corresponding domain, as the future representation is domain agnostic. Instead, it impacts domains that need plenty of data to learn. In conclusion, we propose a domain-independent user simulator with transformers TOIS. We design domain-independent input and output feature representations. Our model outperformed the variational hierarchical sequence-to-sequence user simulator, the state-of-the-art data-driven user simulator. Besides, TOIS is comparable with the agenda-based user simulator, a rule-based user simulator, even though it is based on carefully designed domain-dependent rules. In comparison to previously domain-dependent user simulators, TOIS can handle unseen domains without feature modification or model retraining, even with fewer training samples based on the result of zero-shot transfer experiment. In future work, we'd like to learn natural language generation to make TOIS more human-like and apply reinforced learning to this model to improve its performance. This work is part of the European Research Council funded project DIMO. Thank you for listening and look forward to your questions.
Thank you very much. Thank you so much. I think we can bring everyone, all the speakers back. First of all, thanks a lot for all the very interesting presentations. And maybe we can briefly discuss a couple of questions. One of them, I will jump directly to back to what I asked to Aldo, or a bit more broader. What do you think are the limitations of the current simulation processes, and what are the things that they don't take into consideration so far, and how could we make this happen? So maybe the three simulation people, but also the meta evaluation. Zeyang, you can also comment on having evaluated evaluation measures. What do you think of the simulations? But maybe I'll start with Aldo, Alexandre, and Hsien-Chin to think a bit on what is missing from the simulations.
All right. So, well, I think to understand what is missing in the simulation, we need to discuss for what you want to use the simulation, right? So what I think we should start including more in the simulator are, of course, things that may be relevant for the modeling of the actual search task or conversational task. We could think of including many variables, but then the more variables we include, the more complicated and convoluted the simulator becomes, and that wouldn't allow us to basically make that much progress. So what I would suggest is we should, maybe come up with some hypotheses about what what is the feature that we think should be included, and then test whether that would make progress in a way for the conversation or for the simulator itself. If I can suggest one feature that is right now, I think, not looked at much, is the difference between that exists between spoken and written language. So right now, most of the data sets, most of the simulators are based on written language, and I believe, as it is well known, right, in linguistics, there are many signals, right, that we can exploit in the spoken language that are not exploited. For example, the uncertainty of the user in articulating certain words or certain sentences. So I would.
Right.
This is something that I'm starting to look at.
Okay, cool point. Alexandre, what is missing from your simulator?
Well, we have a paper under consideration right now that looks at cooperativeness and patience in a more subtle way, looking at what happens if that varies as a conversation progresses. So just it's a pretty simple modification, but so like Aldo said, it's a baby step. It's a small improvement, and that's very feasible. It's easy to do, but what's been challenging when we've thought about doing more interesting things. Well, your suggestion, for example, having some kind of hierarchical intent for both, where you'd have that, I guess, for both the user simulator and for the system. Then you start to get into representation challenges of how do you represent that within the user simulator? How do you represent that within the system? And then we found that that's harder. That's a bigger step. So doing these simple things, it's easier. But for us, at least, just even thinking about doing more complex things in terms of representation of intent, dialogue, etc., is difficult.
Right. All right. Cool. Thanks. Hsien-Chin, you showed a simulation that is different from the other two, in the sense that it was more on better defined tasks than the more information-seeking tasks that Aldo and Alex tried to simulate. What do you think about your simulator? Could it be? Is it something that is missing? And also, could you envision it being applied in a domain of information-seeking conversations, where maybe ontologies are not even part of the input?
Yeah, I agree with Alexandre that the user intent is very complicated to model. And like in our case, there's only two, like inform and request. But if we can, sometimes the user they don't have a clear mind to find a restaurant or a hotel. So how to model this kind of behavior, I think is quite difficult. And the user may rephrase their sentence, and we work on semantic level. This kind of things is not modeled yet. And I think there's one more thing is very interesting, that the user would try to make the task successful. So how to model the recover process from the user is a challenging task for me.
Right. Thanks a lot. Are in any of the simulations, is the user making any mistake? For example, giving a negative answer when he should have given a positive answer, or correcting an action but not in the most appropriate way?
Yeah, of course.
Sometimes users do not clearly know what to answer, right? Sometimes we have this I don't know thing, but maybe they actually make mistakes as well.
But I think this kind of behavior is worth to have, because the system should be able to deal with this kind of things, and it can recover back, or it can find another solution for the user. So I think this kind of mistake behavior is good for the user simulator.
Okay, Zeyang, let me come to you. You're muted. You can unmute yourself. I'm wondering if so. You build this meta evaluation framework to evaluate evaluation measures, but your framework is a bit of agnostic on what is happening in the background, right? It takes the metrics, the numbers, the values that the metrics bring, and then it looks at discriminative power, predictive power, so on and so forth. Do you think that the simulations that the three people proposed here could enter in your framework and be evaluated on their discriminative? I mean, they run the simulations most of the time for training, but we could run them for evaluation, right? Do you think you could take them and talk about their discriminative power or predictive power?
Because my meta evaluation framework is mainly focused on the single term, and we also considered multiple term, but multiple term we didn't have a good way to aggregate each term. So in current stage, we only use the session-based metric to aggregate each turn's evaluation and cooperate together to meta evaluate that. But I think user simulator is a good way to make evaluation of multi-term conversational search possible, because I think using the simulators we can capture the user's information needs and the information flow during the conversational search, and we can compare the reference and the candidate response. I think it's a possible way to and a good direction to get them together.
All right, thanks a lot. I think I would like to thank you all and stop here this interesting discussion. I wish we were in some common location and we could have a coffee now and continue the conversation. There is a next session coming up, and I think it does include dialogue evaluation as well, and breakdown detection, which is very close to these mistakes, let's say, that the system does in this case. But thank you very much, all of you, for taking the time being here, even in the difficult time zones, and enjoy the rest of the day. Thank you very much.
Yeah, thank you to all our speakers. Thank you to Evangelos. Great way to start today's session. We will be live in a couple of minutes for the user satisfaction and dialogue breakdown session. So see you there in a couple of minutes.